everyone, these are the operations with scientific notation guided notes. Let's get started. Scientific notation is a way to write really large or really small numbers in a more practical way. For example, the distance between the Earth and the Sun is 92,600,000 miles. The diameter of a hydrogen atom is this number right here. That is 8 zeros right there. Working with really large or really small numbers can be difficult when they are written in standard notation. And standard notation is just this way, the way we would normally write them. Therefore, many scientists will use scientific notation. A number written in scientific notation follows these properties. The decimal term of the number, which we sometimes will just call n, has to be greater than or equal to 1 and less than 10. Also, the decimal will be multiplied by 10 raised to the power of an integer. So let's look at these examples down here in this table and determine if they are written in scientific notation or not. 4.98 times 10 to the fifth. So this number right here is greater than or equal to 1 and it is less than 10. So that checks off for the first requirement, and then it's times 10 raised to the power of an integer. So yes, that is written in scientific notation. 0.498 times 10 to the fifth. This number right here is not greater than or equal to 1. Even though it's times 10 to the fifth, which is good, this needs to be greater than or equal to 1. So that is not written in scientific notation. 4.98 times 9 to the fifth. This number right here is greater than or equal to 1 and less than 10, but it's not times 10 right here. So that is not written in scientific notation. 49.8 times 10 to the fifth. This number right here needs to be greater than or equal to 1 and less than 10. It is greater than 10, so that does not work. This part right here works, but the first part will not. So it is not written in scientific notation. Right here, 4.98, that is greater than or equal to 1 and less than 10 times 10 to the negative fifth, which works because it's times 10 raised to an integer. Let's learn how to write numbers in scientific notation. Remember that scientific notation contains two parts. It's the decimal and then the power of 10 part. First, let's look at the distance between Earth and the Sun, which is 92,960,000 miles. To obtain the decimal part, we will move the decimal until we have a number between 1 and 10. So with this number, the decimal is right here, and we're just going to slide it over until we have a number between 1 and 10. And I'm going to stop it right there because that will give me 9.26. So by moving the decimal to the left 7 place values, we made the number smaller by 10 to the 7th. Because remember, every time I move it over, that's another times 10. So going over 7 would be 10 to the 7th smaller. Therefore, we will multiply 9.296 by 10 to the 7th, so the numbers are equal in value. So 92,960,000 is the same as 9.296 times 10 to the 7th. Let's look at the distance between Earth and Neptune, which is about 2,700,000,000 miles. The decimal portion of this number in scientific notation is, my decimal is right here, and I'm going to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9. If I stop it right here, that gives me the decimal of 2.7. 2.7 is greater than 1 and less than 10. By moving the decimal to the left 9 place values, we made the number smaller by 10 to the 9th. Therefore, we multiply 2.7 by 10 to the 9th, so the numbers are equal in value. So 2,700,000,000 is the same as 2.7 times 10 to the 9th. The speed of light is approximately 300 million meters per second. Let's write this number in scientific notation. So if I move my decimal, it's right here. I'm going to move it 1, 2, 3, 4, 5, 6. If I stop it there, it would be 300. 7. If I stop it there, it would be 30. I'm going to go one more. Stop right there, 8. That is 3, which is greater than or equal to 1 and less than 10. So the decimal portion of this number is 3. By moving the decimal to the left 8 places, we made the number smaller by 10 to the 8th. Therefore, we multiply 3 by 10 to the 8th, so the numbers are equal in value. 300 million equals 3 times 10 to the 8th. Practice. It's giving us the number in standard notation, and we need to write it in scientific notation. 652 million. I need to move my decimal until I have a number that's greater than or equal to 1 and less than 10. So I'm going to move it 1, 2, 3, 4, 5, 6, 7. That's 65.2. Move it one more. That gives me 6.52. And I made it smaller by 10 to the 8th. So my scientific notation is 6.52 times 10 to the 8th. 32 million. So we're going to move it 1, 2, 3, 4, 5, 6. If I stop it right here at 7, that's 3.2. And that will be greater than 1 and less than 10. So I made it smaller by 10 to the 7th. My scientific notation will be 3.2 times 10 to the 7th. 1,560,000,000. Let's move my decimal. So I have it 1, 2, 3, 4, 5, 6, 7, 8. That's 15.6. Move it 9. Gives me 1.56. That's greater than 1 and less than 10. I made it smaller by 10 to the 9th. So my scientific notation is 1.56 times 10 to the 9th. Remember that scientific notation is also used for very small numbers. To see what small numbers look like in scientific notation, let's first complete the table below. What pattern do you notice on the top? Okay, so we're going to actually go to this table first. So I have 10 to the -4th, -3rd, -2, -1, 0, 1, 2, 3, 4. So 10 to the 4th is 10,000, 10 to the 3rd is 1,000, 10 squared is 100. So notice that as I go this direction, I'm actually dividing by 10. I'm going down by a 10th every time. We are going to say that pattern will continue. So 10 divided by 10 is 1, divided by 10 again is 1/10, divided by 10 is 100th, divided by 10 is 1,000th, and divided by 10 again is a 10,000th. And now we're just going to write those numbers as fractions. So that would just be 1 and 1 over 10, 1 over 100, 1 over 1,000, and 1 over 10,000. So going back up here to these questions, what pattern do you notice on the top row? So I noticed that the exponents, just the exponents right here, are increasing in power by 1 from left to right. What pattern do you notice on the second row going from right to left? So I notice that the number is divided by 10 each time. From the table, we notice that 10 to the -1 is the same as dividing by 10. 10 to the -2 is the same as dividing by 100, etc. Now let's write the number right here in scientific notation. The decimal portion would be, so we're going to do the same thing. We're going to move my decimal until I have a number that's greater than or equal to 1 and less than 10. So 1, 2, 3, 4. I'm going to stop it right there, and that will give me 4.6. By moving the decimal to the right 4 place values, we made the number larger by 10 to the 4th. Therefore, we multiply 4.6 by 10 to the -4. Recall, this is the same as dividing by 10 to the 4th. So the numbers are equal in value. So we're going to have 4.6 times 10 to the -4th. And that's going to move the decimal this direction because we're going to be dividing to make the number smaller. Let's write this number right here in scientific notation. So we're going to move the decimal 1, 2, 3. I'm going to stop it right there because that gives me 5.74. And I moved it 3 spots. We made the number larger by 10 to the 3rd. Therefore, we multiply 5.74 because I want to make the number actually smaller. So I'm going to go 10 to the -3. So the numbers are equal in value. So it's going to be 5.74 times 10 to the -3. And that's dividing by 10 3 times and moving the decimal to the left 3 times. Practice. We're going to write these numbers in scientific notation. So let's first move my decimal. 1, 2, 3. That's going to give me 3.4, which is between 1 and 10. I moved it 3 times. And so it's going to be 3.4 times 10 to the -3. Let's look at this one. I'm going to move it 1, 2, 3, 4 right here. 4.12 is between 1 and 10. And I move that 5 times. So it's going -5 because I want to make 4.12 smaller. So divide by 10 5 times. And so it's 4.12 times 10 to the -5th. Let's go on to the next one. 1, 2, 3, 4. I'm going to stop it. So it's 5.9. which is between 1 and 10. I moved that 4 times, so 10 to the negative 4. So I have 5.9 times 10 to the negative 4th. Explain why 5.2 times 10 to the negative 5th is a number greater than 0, but less than 1. So if I have the number 5.2 times 10 to the negative 5th, that means I am dividing by 10 5 times. So I'm going to divide by 10 once, twice, 3, 4, 5 times. My decimal is right there, and these are all filled with zeros. I put a 0 on that side just as a placeholder. So notice that number is still positive. It's still greater than 0, but it's less than 1 because I divided by 10 5 times. For each number, circle whether the number is less than or greater than 0, and if the number is less than or greater than 1. 2.35 times 10 to the 5th. If I'm timesing by 10 5 times, so 1, 2, 3, 4, 5, that's going to be about this. That's going to be this. That number is still going to be greater than 0, and it's also going to be greater than 1. 1.09 times 10 to the negative 3rd. I'm going to be dividing by 10 3 times, so 1, 2, 3. Again, it's still a positive number, but in this case, it will be less than 1. 6.23 times 10 to the negative 2, 1, 2. Over here, it's going to be still greater than 0, but less than 1. 9.3 times 10 to the 4th, I'm multiplying by 10 4 times, 1, 2, 3, 4. Here's my decimal, so greater than 0 and greater than 1. Now, let's practice writing standard notation given scientific notation. Look at the number 1.8 times 10 to the 7th. This is saying to take the number 1.8 and multiply it by 10 7 times. Recall that since our number system is based on 10, every time you move the decimal to the right, you are multiplying by 10. Therefore, you will need to move the decimal to the right 7 times. So practice. 2.35 times 10 to the 5th. I'm multiplying by 10 5 times. So I'll move the decimal 5 times. So 1, 2, that's 235, 3, 4, 5. It looks like I'm going to add 1, 2, 3 zeros. 1.09 times 10 to the 3rd. I'm going to move the decimal 3 times. I multiply by 10 3 times. So 1, 2, 3. I'm going to add 1 0. 6.23 times 10 squared. Move it over twice. 1, 2. So 623. 9.3 times 10 to the 4th. So 1, 2, 3, 4. I'm going to be adding, 3 zeros. Let's analyze the number 1.8 times 10 to the negative 5th. Recall that multiplying by 10 to the negative 5th is the same as dividing by 10 to the 5th. Again, since our number system is based on 10, every time you move the decimal to the left, you are dividing by 10. In this case, you will move the decimal to the left 5 times. 1.8 times 10 to the negative 5 in standard notation. So if we move the decimal to the left 5 times, we have 1, 2, 3, 4, 5. So that gives us 4 zeros. And I will put the 0 in front as a placeholder. 4.3 times 10 to the negative 6 is greater than 0, but less than 1. Multiplying by 10 to the negative 6 is the same as dividing by 10 to the 6th. Our number system is based on 10. Every time you move the decimal to the left, you are dividing by 10. In this case, you will move the decimal to the left 6 times. So if I move it to the left, 1, 2, 3, 4, 5, 6, it gives me 5 zeros after the decimal. And again, I place the 0 in front as a placeholder. 2.35 times 10 to the negative 5th. Let's move it. 1, 2, 3, 4, 5. Here's my decimal. I'm going to be adding 4 zeros in front of the 2. 1.09 times 10 to the negative 3. 1, 2, 3. Adding 2 zeros. 6.23 times 10 to the negative 2. 1, 2. Adding 1 0. And 9.3 times 10 to the negative 4. So 1, 2, 3, 4. I'll be adding 3 zeros. Adding and subtracting using scientific notation. If two numbers written in scientific notation are raised to the same base, 10 power, then you may add or subtract the digit part. So, for example, 6.5 times 10 to the 7th plus 5.2 times 10 to the 7th. Notice that they are raised to the same 10 base, meaning they're both raised to 10 to the 7th. So I can just add 6.5 plus 5.2, and that gives me 11.7 times 10 to the 7th. You need to notice this. The sum above is not written in proper scientific notation and needs to be adjusted. So once I added them, I got 11.7 times 10 to the 7th. But 11.7 is greater than 10, so that's a problem. So I'm going to need to adjust that for my answer. I'm going to need to move the decimal over one more time. So it says 1.17, and I need to change my exponent to be 10 to the 8th since I moved the decimal one more time. 6.5 times 10 to the 7th minus 5.2 times 10 to the 7th. These are both 10 to the 7th, so now I can just subtract them. 6.5 minus 5.2 gives me 1.3 and then the same power. And that is written in scientific notation, so I don't need to adjust it. Okay, so let's practice. Notice that all these problems have the same base 10 power within the problem, so I don't need to do any adjusting there. So I can simply add or subtract the decimals. So 2.35 plus 3.15, let's just add those, and that gives me 5.50. Now 5.50 is written in scientific notation, so it's 5.50 times 10 to the negative 5th. So 7.09 plus 4.92, that gives me 12.01. Now, that is not scientific notation. I need to move the decimal over one spot, so I'm going to write 1.20. Now, the reason why I'm not going to write a 1, this has 3 digits, this has 3 digits. I'm going to keep my answer with 3 digits. So 1.20 and times 10. Now I did move my decimal one more spot, so it's going to be times 10 to the 4th. So let's now subtract 6.23 minus 2.1, and that gives me 4.13, which is between 1 and 10. So nothing else changes there. So 4.13 times 10 squared, and then 9.3 minus 5.6 gives me 3.7, and that's between 1 and 10, so we'll keep my power of 10 to the negative 8th. If two numbers written in scientific notation are not raised to the same base 10 power, then you will need to rewrite them, so they are written in the same base 10 power. 6.5 times 10 to the 3rd plus 5.2 times 10 to the 5th. Notice the powers of 10 are different, but you can use the product rule and write 10 to the 5th as 10 squared times 10 cubed. This is more useful because the first number also uses 10 cubed. So let's rewrite the problem. 6.4 times 10 to the 3rd plus 5.2 times 10 squared times 10 to the 3rd. So we're going to try and make it so it is 10 to the 3rd power. So 5.2 times 10 squared, now remember that came from right there, is 520 times 10 cubed. I got 520 by moving that decimal over 2 spots, 1, 2. So now it says 6.5 times 10 cubed plus 520 times 10 cubed. Now they have the same power of 10, and you can find the sum. So I'm going to do 6.5 plus 520, which is 526.5 times 10 cubed. Again, notice that the sum of the two numbers is not written in scientific notation. This will need to be changed. So I need to move my decimal over 2 more spots. So 1, 2. So 5.265 times 10 cubed. And let's keep the same number of significant digits. There's 2 digits there, 2 digits in the problem. So I'm going to keep 2 digits and I will round it. So 5.3 times 10 cubed. 4.2 times 10 to the 7th plus 1.9 times 10 to the 4th. Rewriting 1 so they can use the same power of 10. So I'm going to rewrite this with a power of 10 of a 4. So that's going to be 4.2 times 10 to the 4th times 10 to the 3rd. Remember with product rule, if I sum those, they need to equal 7. So regrouping, let's regroup this. So let's do 4.2 times 10 cubed, that section right there, and that will be times 10 to the 4th. So simplifying, 4.10 cubed is going to move the decimal over 3 spots. So 1, 2, 3. So that number is 4,200 times 10 to the 4th. And I'm adding that with 1.9 times 10 to the 4th, and that equals 4,201.9 times 10 to the fourth. Now changing to scientific notation, I need to move my decimal over 1, 2, 3 spots. So it's 4.2019, and I moved it over 3 spots. So I'm adding 3 more, so it's 10 to the 7th. Now I need to use the same number of significant digits. So we're going to do 4.2 times 10 to the 7th. Simplify the expressions below, and it's kind of guiding me through it: rewriting, regrouping, simplifying, and scientific notation. So 2.35 times 10 to the 6th plus 3.15 times 10 to the 4th. So let's write it so they have 10 to the 4th. So 10 to the 6th is going to be 10 to the 4th and 10 squared. 2.35 times 10 to the 4th times 10 squared. And then I'm adding that with 3.15 times 10 to the 4th. Let's regroup that here. So 2.35 times 10 squared times 10 to the 4th plus 3.15 times 10 to the 4th. 2.35 times 10 squared is 235 times 10 to the 4th plus 3.15 times 10 to the 4th. And that equals, so I'm adding those together, I get 238.15 times 10 to the 4th. Changing that to scientific notation, 2.3815, I need to move the decimal over 2 spots to get it into scientific notation. So that's 2.3815 times 10 to the 6th, because I moved the decimal over twice. Using significant digits, I get 2.38 times 10 to the 6th. Okay, let's do this one here on the bottom. Let's rewrite it so I have the same powers. 10 to the negative 7 will be 10 to the negative 5, and then 10 to the negative 2. So I have 2.1 times 10 to the negative 5 minus 6.2 times 10 to the negative 5 times 10 to the negative 2. So that gives me 2.1 times 10 to the negative 5 minus, we're going to group this together, 6.2 times 10 to the negative 2 times 10 to the negative 5. So 2.1 times 10 to the negative 5 minus 6.2 times 10 to the negative 2. I'm going to go over 2 spots. So that's going to be 0.062 times 10 to the negative 5. 2.1 minus 0.062 gives me 2.038 times 10 to the negative 5. That is written in scientific notation, so I don't need to change that. I'm just going to change my significant digits to 2. So 2.0 times 10 to the negative 5. Multiplying and dividing using scientific notation. To multiply and divide numbers in scientific notation, we can use the exponent rules. Let's first look at multiplying x to the m times x to the n. Remember, that's the same as x to the m plus n. Using the exponent rule above, 2.3 times 10 cubed times 1.2 times 10 to the 4th. We're going to regroup it. So I have my decimals and then my powers together. 2.3 times 1.2 times 10 to the 3 plus 4. And that's using the exponent rule. So simplifying that, 2.3 times 1.2 is 2.76. 10 to the 3 plus 4 is 10 to the 7th. And then rounding to the significant digits, I get 2.8 times 10.7. Okay, so let's do that with this. 4.2 times 10 squared, 3.1 times 10 to the 4th. So I have 4.2 times 3.1, I'm just regrouping, and then I have 10 squared times 10 to the 4th. So using my exponent rule, 4.2 times 3.1, 10 to the 2nd times 10 to the 4th is 10 to the 2 plus 4, which is 6. Now if I multiply 4.2 times 3.1, that gives me 13.02 times 10 to the 6th, which is true, just not written in scientific notation. So I've got to move the decimal over one more spot. So that's going to be 1.302 times 10 to the 6th. And then changing that to significant digits will be 1.3 times 10 to the 6th. Okay, now with division, recall that x to the m over x to the n equals x to the m minus n. So using the exponent rules above, we have 7.2 times 10 to the 8th divided by 1.2 times 10 to the 3rd, regrouping, so I have my decimals and I have my powers. Exponent rule, keep my decimals, so it's going to be 10 to the 8 minus 3. So simplified, 7.2 divided by 1.2 is 6 times 10 to the 5th, which is 8 minus 3. And then my significant digits, I need 2, so I'm going to add the 0.0. Okay, so 6.3 times 10 to the 7th over 1.5 times 10 to the 4th. Let's regroup that. So I have 6.3 over 1.5, and then I have 10 to the 7th over 10 to the 4th. Applying the exponent rule, I have 6.3 over 1.5, and then I have 10 to the 7 minus 4. 6.3 divided by 1.5 is 4.2, times 10 to the 7 minus 4 is 3. And that is written in scientific notation, so I don't need to change anything. Practice. 3.5 times 10 squared times 2.5 times 10 to the 6th. I'm going to multiply my decimals. 3.5 times 2.5. That gives me 8.75. And then my exponents, 10 squared times 10 to the 6th, gives me 10 to the 2 plus 6, which is 8. And that is written in scientific notation, but I have two significant digits, so that's going to be 8.8 times 10 to the 8th. So 9.2 divided by 2.5 is 3.68 times 10 to the, I'm going to go 9 minus 3, which is 6. So then using significant digits, it's going to be 3.7 times 10 to the 6th. The population of New York City is about 8 times 10 to the 6th, and the population of the state of Wyoming is 6 times 10 to the 5th. We want to determine about how many times bigger the population of New York City is than the population of Wyoming. Let's set up a division problem. So we're going to divide 8 times 10 to the 6th divided by 6 times 10 to the 5th. And that's going to tell me how many times bigger it is. So 8 divided by 6 is 1.333, etc. And that's going to be times 10 to the 6 minus 5 is 1. So to make sense of that, I don't need to answer in scientific notation because it's just asking me a question. How many times bigger? So 1.3 times 10 to the 1st is going over 1. That's 13 times bigger. The population of New York City is more than 13 times larger than the population of Wyoming. An atom measures about 10 to the negative 8 centimeters, and a flea measures about 2 to the negative 1 centimeters. Let's determine about how many times bigger a flea is than an atom. So we're going to set up a division problem. So 2 times 10 to the negative 1st divided by 10 to the negative 8th. So 2 divided by 1 is 2. Then we're going to do negative 1 minus a negative 8, which is negative 1 plus 8, which equals 7. So that's going to be 2 times 10 to the 7th, which equals 2, 0, 0. So 7 zeros, because I'm moving the decimal over 7 times. So that's 20 million. So a flea is about 20 million times larger than an atom. The distance from the Earth to the Sun is about 9 times 10 to the 7th miles. The distance from the Earth to the Moon is a little more than 2 times 10 to the 5th miles. About how many times more is the distance from the Earth to the Sun than the Earth to the Moon? So let's set a division problem. So 9 times 10 to the 7th divided by 2 times 10 to the 5th. So 9 divided by 2 is 4.5 times 10 to the 7 minus 5 is 2. So slide that over 2 spots and I get 450. So it's about 450 times further to the sun than it is to the moon from Earth. Okay, everybody, that's it for today. Thank you.